I'll start recording. Okay, so right here I can see that I have my chapter 15 ready. The recording has started, and so we'll go through this. Chapter 15 deals with lipids, and as we're dealing with lipids, we're going to go over functional groups that tie back into lipids. So we're told here lipids are biomolecules that are soluble in organic solvents and insoluble in water. So we're getting straight to the information. Lipids, the structure of the lipids make them soluble in organic solvents. When they say organic solvents here, they mean nonpolar. So lipids are mostly nonpolar versus polar. And the saying soluble in water means that they're not soluble in polar compounds because water here represents polar. Lipids are defined on the basis of the physical property, not by a particular functional group. Thus, they have a variety of structures and functions. So we have a lot of different lipids out there. And for the group that are studying it, the biochemists, they group them based on similarities in physical properties, not based on functional groups. Okay? So all lipids contain many nonpolar carbon-carbon bonds and carbon-hydrogen bonds. We've mentioned this before. We're mentioning it again in this context because it applies here. Wait, hold on a second. Okay, I forgot my water. Um, and a few polar bonds resulting in their water insolubility. What they're saying here is that lipids contain more nonpolar bonds than they do polar bonds. So you have a greater nonpolar character, right, from the nonpolar bonds compared to polar characters. So the whole molecule behaves as a nonpolar, even though you do have a few polar bonds. Okay, moving on. When we're categorizing lipids, we have two main categories of lipids. You have the hydrolyzable ones, and remember we mentioned hydrolyzable before. Hydrolyzable just means that you're using water molecule to break apart, right? We talked about this before with the glucose, and now we're talking about it here again in this context here. Hydrolyzable liquids can be converted into smaller molecules by hydrolysis with water. So adding water breaks that bond. Okay, so these are the examples of the hydrolyzable lipids. We have three categories. We have waxes, triacylglycerol, phospholipids. Okay, and we're going to go through and study each section at a time. Remember, all of these three are hydrolyzable. So if you want to break them down, all you need is water and some kind of catalyst, and you can break this down. Okay, so we're going to be starting with once we get to that part, before I get to the categories, we need to talk about the non-hydrolyzable lipids. The non-hydrolyzable lipids cannot be cleaved into smaller units by aqueous hydrolysis. You can't just add water to these and catalysts and hope they break down. Okay. Example of non-hydrolyzable liquids or lipids are steroids and fat-soluble vitamins. And so we'll talk about this down the road. These are A, D, E, K. When I was taking biology and I was learning these, I memorized them as ADEC or ADEC. Okay, so vitamin A, D, E, and K. Okay, now we're focusing on the hydrolyzable fats. Fatty acids are examples of hydrolyzable fats. These hydrolyzable lipids are derived from fatty acids. So with fatty acid, we have to go back to carboxylic acids, right? Remember, organics is a step up from I mean, biochemistry is a step up from organics. When we're dealing with fatty acids, we're dealing with really acids, which is organic acids. And organic acids are your carboxylic acid. We mentioned that before. These have that functional group of the carbonyl, right? With the hydroxide on one side, and then the other side you have a carbon. Now we're told that with these fatty acids, yeah, you have a functional group that's a carboxylic acid, but the rest of the molecule has so many carbons. You have a long carbon chain, and we have between 12 and 20 carbon atoms in that long carbon chain. So here we have an example of a carboxylic acid that has, let me see, let me do some math here. We're told that the end carbon is CH3, so that's one, and then we have 14 of these pieces, so 1 plus 14, and then we have this carbon right here plus 1. So essentially we have what, 16? In palmitic acid, we have 16 carbons total. So here's an example of a molecular structure, or at least molecular model of a fatty acid. You can see the long carbon chain, which is the nonpolar portion. Remember, it's nonpolar because it has carbon-carbon and carbon-hydrogen bonds only. And remember, these bonds we decided before they were polar. The electronegativity difference wasn't big enough to make them. Sorry, they were non-polar. The electronegativity difference wasn't big enough to make them polar. Okay. So these are non-polar. Then on this end here, you have polar bonds, right? Remember, you have a OH, that's this bond right here. You have a CO, and then you have CO. And essentially, this end here is the end that is polar, okay? They're using new terms that we haven't seen before until this section, which is hydrophilic. Now, hydro here stands for water, and then philic has to do with loving. So the end of the molecule that's polar is just like water in the sense that water is also polar. So this end that's hydrophilic loves water because remember, like dissolves like attracts like. So in this case here, this end can draw water to itself and it can be drawn by water. The other end hates water, it's like abhors water. And this is hydrophobic. It's not a hateful water, but it's a fear of water. So hydro is water, phobic here is fear. So this end of the molecule fears water. Okay. Now, does the molecule sit there and really have serious anxiety over water? No. But when they're saying fear, what they see in scanning electron microscope, a very powerful microscope, is that the ends that are hydrophobic will move away from water. And when they move away from water, scientists interpret that as a fear of water. Okay. Okay. So we're asked here, in which solvents or solutions will a lipid be soluble? Well, we said a lipid was nonpolar naturally, right? Where is it? This is nonpolar. So in other words, what they're asking you is, of these three, which one is nonpolar? Okay, this is nonpolar. I'll write NP for nonpolar. This is nonpolar. If you have sodium chloride is ionic. Ionic is like an extreme form of polar, right? Ionic is like an extreme polar. Extreme polar. So this lipid will definitely not dissolve in anything that's aqueous, not water, but something nonpolar. So this one here, A and C, work for our answers. Okay, now we're moving on. So we're told here, moving on with our fatty acids, naturally occurring fatty acids have an even number of carbon atoms. That's a very interesting fact, right? You go to a trivia and they say the following, yeah, they can ask you that question. I don't know. I don't do trivia stuff. Saturated fatty acids have no double bond, ergo saturated, right? These are like alkanes. And they're long hydrocarbon chains. Unsaturated, this will be like alkenes and alkynes, right? Like what we learned before. In this context, though, unsaturated fatty acids have either one or more double bonds. So we're looking at the double bond or the alkene functional group inside of within the fatty acid. And for the most part, we tend to see either cis or even trans, because remember, we do have trans fats. Yeah, we have trans fats. So trans fats will have that double bond with the large molecules diagonally across from each other in their long hydrocarbon chain. As the number of double bonds in the fatty acid increases, the melting point decreases. What is being said here is the double causes the molecule to somehow have a lower melting point. Okay? So now we're moving on and looking at this here. Continuing with the case that we're building for the hydrolyzable fatty acid. Our example here is stearic acid. Once again, from the word acid, we get the idea it's a fatty acid. It's a saturated fatty acid. Okay, I know the acid part is this part here. That's the acid molecule. I can see that. It's very obvious. But let's see where it says it's saturated. I'm going to look at all my carbons through here and see that there is no double bond here at all. So yes, correct, it's saturated. Oleic acid. Oh, by the way, the saturated fatty acid has got a melting point of 71 degrees Celsius. That's not very high, but it's high, really high for a fatty acid, right? We're talking about something that's like butter. Okay. Oleic acid has a melting point of 16 degrees Celsius. And this is an unsaturated fatty acid. So unsaturated, where's our double bond? There it is. Where's the acid functional group? Right here. Okay. So we see a double bond here. The double bond is a cis bond, so this would be a cis fat. Now, weirdly enough, cis fats are not called cis fats, they're just called fats. But trans fats are called trans fats because remember, there is a health risk with trans fats. So people want to label it kind of as a warning, like, okay, do you know you're eating trans fats? You're like, yeah, it tastes so good, right? Okay, so moving on, we have linoleic and linolenic acids. These are essential fatty acids, but we don't make them in our bodies, so we have to actually eat them. Linoleic acid is omega-6 acid. If you've ever taken fish oil, right, you may drink it. When I was a kid, I used to have really bad asthma, and one of the remedies, the home remedies that my parents would give me is nasty, nasty cod liver oil. I was like, Lord, why? I'm already sick. Why do I have to go through this and drink this nasty oil? It tasted like oil. It was flat, and then it had a slight fishy flavor. It was not entertaining at all. And they're like, drink that, it'll make you feel better. Did it make me feel better? It made me feel better when I was done drinking it. But yeah, I don't remember seeing a correlation there. But anyway, I think they were trying to get me to have the omega-6 or omega-3. They could have given me pills. I guess they didn't have those. But anyway, you can get these oils, these fish oils in the liquid form, like the one I was given when I was a kid, or you can get in the capsule form because omega-6 and omega-3 is important for your health, for your eyesight, for different things. Lowers cholesterol, things like that. Because of the position of the first carbon-carbon double bond in the nonpolar chain. So omega-3, when we say omega-3, we are referring to the first unsaturated carbon or the carbon-carbon double bond. So weirdly enough, since remember this group of people are not organic chemists, they're still chemists. We claim them as chemists, but they're not organic chemists. Their nomenclature system is very different. So here, instead of numbering from the functional group, they number from the other end. So if you count the carbons, 1, 2, 3, 4, 5, 6, you get to the sixth carbon and there is a double bond, ergo omega-6. So this is just saying a double bond is on the sixth carbon. You have another one down here, but the whole acid is classified based on the first carbon that has the double bond. Okay, so moving on. Linolenic acid, on the other hand, is an omega-3 fatty acid. And you have heard about omega-3 from fish and salmon and things like that. Because of the position of the first carbon-carbon double bond in the nonpolar chain. Again, count from the left to the right, okay? 1, 2, 3, and there we face our first carbon-carbon double bond. Okay. Oh, thank God they say skeletal. Draw a skeletal structure. So we're going to be drawing a skeletal structure for each fatty acid. I am so glad they said skeletal because this is going to be long. You see how huge these molecules are? When I was teaching this on campus, students would say, oh, this is so overwhelming. I'm like, it's just what we learned before, but in a macro scale, in the sense that not in amount, but each molecule is very huge. That's why chemists come up with all these short ways of writing things. They get tired. It's like, come on, okay? So they said skeletal structure. Great. Okay, for the fatty acids. So let me see. For A, I have one carbon here, 1 plus, and then here 16, right? It says this repeating 16 times, and I have one here. So essentially, I have what, 18 carbons? Let me see if I can do this. So for my first one, let me copy this. Erase that. Hold on. Let me copy this. Come on. I need to slow down a little bit. I think I'm moving too fast for the pen. Okay. Move this down. I do have 18 carbons, right? So I'm going to start with the last one being 1, 2, 3, 4. Oops, I forgot. You can't linger with this pencil. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yikes. Hold on. I made this too big. It's been a while. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. This is my 18th carbon. And then here, 16th, 17th, 18th, right? My 18th carbon is essentially the one that's the functional group, carboxylic acid. Okay, dot, 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 dot. And then they want me, so this part is done for the first molecule. Label the hydrophobic and the hydrophilic portion. Okay, doable. This is hydrophobic. This right here, hydrophilic. Okay. Without referring to table 2, which fatty acid has the higher melting point? Oh, okay. Well, I'm not done with both of them. But remember, this will have a higher melting point. Higher. Ooh, how do I spell higher? Higher melting point because it has no double bonds. Okay, when you look at your alkyl group or your long chain, there is no double bonds. That means that it will have a higher melting point. How do we jump from no double bonds to higher melting point? It has to do with how the rest of the molecule is aligned, right? This looks overall straight, right? If I draw around it, it looks linear, straight. So the molecules can compact very closely together. It would be like taking neatly folded t-shirts and trying to pack them. You can pack them neatly on top of each other, right? And pack them very tightly together. That's what creates solids. So in this case here, essentially they are solids because they tightly pack. And for that reason, they have a higher melting point. Okay, what else are we looking at? We're looking at this one right here. And this is essentially, let's draw that one. Woo, let me see how many carbons we have here. 1, this here is 4. Then here we have another one. Then here 1, 2, 3, we have 3, 1 plus 1, 7 plus 7, 1 plus 1. Wow, I am not going to add this in my head. It's been a long week. 1 plus 4 plus 1 plus 3 plus 1 plus 7 plus 1. 18. Okay. Structure B has 18 carbons. So let's see. This carbon here, the double bond, is carbon number, I'll make this cis. This is carbon number, this is 1, and so this would be carbon number 5, 6, 7, 8, 8, 9. Oh, okay. So I can keep going until I get to that. I'm going to need this part here, all of this, copy it. Okay, so let's do this. I know I have 18 carbons total, right? So I'm going to go 1, 2, 3, 4, 5. This is carbon 5. Then I have to draw my double bond here. 6, 7, 8, 9. Oh, 9. Hold on. Oh, 7, 8, 9. Then my double bond will be up here, right? No, my double bond is between 8 and 9. Oh my goodness. Okay. I wasn't paying attention. I have to go back. Can I erase this one thing? But, ooh, okay. I'm glad I took a pause there. Okay, so between 8 and 9, right, we have our next set of double bonds right here. So that's how it goes. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let me shrink this a little bit because I used too much space. Okay, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so we have our 18 carbon fatty acid here. That's why I said 18, right? Yep, there it is. So, as usual, this whole portion here will be our non-polar hydrophobic. And then here, this small section here will be polar hydrophilic. Okay? And then I already said this is going to have a lower melting point because of double bonds. Okay? Okay, what else was I supposed to do? Oh, I did pretty much everything that was asked. Okay, so DHA, this is actually a common fatty acid that's important for, I think, pregnant women, because at some point I was looking for some vitamins and I saw that one at Walmart on the shelf, DHA for pregnant women, and I was like, oh, okay, that's interesting. I think it's important for the formation of the baby's brain, because you know how our brain cells has a lot of fatty tissue in there, the membrane in the brain. Anyway, membrane in the brain. Okay, so the technical term for DHA is 4, 7, 10, 13, 16, 19 docosahexaenoic acid. Say that very fast. This is a common fatty acid present in tuna fish oil. Draw the skeletal structure for DHA. So they gave you DHA. This is DHA right here. Once again, really? We got to do this? I guess I added it here. I could have taken it off, but I added it here. Okay, let me number this so I can know what carbons to put my double bond on. 1, 2, 3, 4. So 3 and 4. 5, 6, 7. So 6 and 7. 1, 2, 3, 4, 5, 6, 7. 8, 9, 10. So 9 and 10. 11, 12, 13, 14, 15, 16, 17, 18, 19. So we got 12, 13, 15, 16, 18, 19, 20, 21, 22. Wow, we got 22. Okay, so I start here. 1, 2, 3, 4. Oops, I already did it wrong. 1, 2, 3. Double bond. 3 and 4. 5, 6, 6 and 7, 8, 9, 9 and 10, 11, 12, 12 and 13, 14, 15, 15 and 16, 17, 18. Let me make this a little smaller because I'm running out of room. Okay. 16, 17, and 18. Wait, 16, 17. Oh, sorry. I did the numbering wrong. This is supposed to be 18, right? Because I was about to say, what? There's a pattern here. 18, 19, double bond. And then 20, 21, 22, double bond. O, O, H. This is 22. 19, 20, 21, 22. Yeah, there. So, again, this is 1, right? Draw the skeletal structure. That's done. Give the omega N designation for DHA. This is going to be omega 3, right? Because the 3 is the first carbon that we get to from the left. Okay, give the omega N designation. We don't have to draw this. Yay. Okay. Omega N designation for the following oleic acid, arachidonic acid. Arachidonic acid. Okay. Oleic acid. This is our first carbon, and then we have 7 more, making this our 8th, right? No, sorry. We have 7 more, making this our 9th. I can't count. My goodness. 1 plus 7, that makes 8. And then this one here is 9. So this is 9. So this is going to be omega 9. The omegas comes in threes, so you have omega 3, omega 6, omega 9, omega, yeah, they're in threes. Okay. And then this one here, let's see, this is our first carbon, then we have 4 more, and then we have, they say 2 of these, right? But the first time we encounter the first carbon, that's carbon what? This is carbon 6, so this would be omega 6. Okay. So we got omega 9 there, we got omega 6 here. I don't have to draw the whole thing. I can move on to talk about waxes. Waxes are esters formed from fatty acids reacting with high molecular weight alcohol. So the general structure of a wax is actually an ester. Remember how we saw esters before? Esters were formed when we had carboxylic acid plus alcohol. These gave us esters. Okay? So, taking you back, see, in the organic portion, this functional group wasn't just called a fatty acid, it was called a carboxylic acid. But we're seeing once again, acid plus alcohol gives us esters. So this is going to be esters, or what they call here, wax. Okay? So once again, this bond breaks, right? Remember, the leaving group was like the teacher going off, and then the sub comes in. So that this bond breaks, then the OR is the sub that comes in, and then these two go off together to form water. Okay, let me get some water right here. And once the OH is gone, the OR comes in to replace the OH, right? Okay, so now we're kind of detouring a little bit and talking about spermaceti wax. So spermaceti wax is isolated from the head of sperm whales. And I remember reading about this a long time ago and was very sad because when they say isolated, that means the whales have to be killed, because it's not like the whale will be like, oh, let me see, let me take this out from my head and give it to you. They have to kill the whale. And then they use this wax after they kill the whale. Very sad. I'm like, can we like get wax from elsewhere? They use this wax to make fine I can't speak. Fine candles. So like uppity nice candles. Okay. Okay. That one was kind of, I'm like, okay, I don't use fine candles. I'm okay. I'm good. I'm not causing a whale to die. Then they said they use it for sometimes lotions and stuff. I'm like, oh dang, I use lotion. I haven't checked to see. I have never used any lotion that has this stuff. But when they mention the wax in the fruits, you know how Walmart, I say Walmart because I shop there a lot, okay? But when you go to those really nice grocery stores, detour a little bit. When I first came to America, I got to Walmart. That's why I'm so in love with Walmart, okay? That was my first store. So I kind of imprinted on that, or that imprinted in me. I bonded with Walmart. I was like, why do the foods here look so pretty? Why do they look so good? Like, not in a good way, good. They look so like dressed up, the like photoshopped. That's how it felt to me, because I'm like, why are they all shiny and stuff? Why they look polished, like wax? And then my friend was like, that's how the food looks over here. I'm like, I'm not gonna eat that. I want my food to look natural. A little dented on the side, a little raggedy, but I want my food to look like it came from the earth. This looks like it came from the studio. And she looked at me like, well, you're not going to survive in America. I'm like, I guess I'm not going to eat. Well, I had to adapt, right? I bit into the apple. I'm like, why does it taste like it has a film on it? It's a wax. Why do we have a wax? The apples at home don't have all that stuff that just came from the tree. They barely washed them. Anyway, that wax they put on the apples, when you bite into the apple, you don't really taste it very well until you kind of chew some more. That's from this stuff, y'all. I mean, I'm sure now they use something else, but that's what they kind of use it for. They use wax to coat foods and stuff. Yeah, it makes you think twice, huh? By organic stuff will not have all this stuff on it. Anyway, I'm going to get off my soapbox. Moving on. So here we're seeing an actual reaction between palmitic acid and you have an alcohol here. Notice that these are all, we're in the section of grease or fat. So everything here will be greasy or fatty. These long carbon chains are, nonpolar or fatty. Again, over here, nonpolar. So even though you have a polar functional group here, the nonpolar behavior, once again, nonpolar characteristics is greater than the polar. So the overall molecule behaves nonpolar characteristics, right? So yeah. So this is a major component of spermaceti wax. I can't pronounce certain words, but a good thing is that you can synthesize this. So this can be synthesized. Of course, it's not as good as a natural thing, but I would rather synthetic if that means that the whale gets to live, right? Okay, so here we have three of these. I'm just gonna draw one. Do I really need to do all three? You can apply what I do for the one to these other two, right? Okay. Draw the structure of a wax formed from stearic acid and each alcohol. So I'm just going to do it one time. Once again, the way I have these PowerPoint designed, it was supposed to be in a class where I have three people come to the board and each person works on one. Okay, let's see. I want to put my carboxylic acid to the left, so I'm going to write it here. CH3, CH2. We got 16 of these, man, to make it fatty. I'm going to draw this out like that. And then I got my OH here. This is my group that's leaving, right? And it's going to be replaced by, oh, I write so large, and then I run out of the room and I have to shrink this. That's okay. It's okay. It's replaced by, I guess, the first one here. I'm going to write this just like this, CH3, CH2. I think we've gotten to the point where we understand what's going on so we can kind of follow along, right? So remember, this part here, let me highlight it. The OH is replaced by this part, right? So on the product side, can I get this here? I need to shrink this even further, y'all. I think you can get it in there, at least that much. Okay, let's see. So CH3, CH2, 16, carbonyl carbon, and then O, CH2, 9, CH3, right there. Oh, plus water, plus water. Okay. So this right here is your wax. The wax is the ester that's made. So we're told here waxes form a protective coating. Before, people were artificially putting on fruits to make them look so pretty and picture perfect. Protective coatings were used naturally on feathers. Birds naturally have this to prevent them from, if you notice, ducks are in water and they come out and they look dry, right? They have that dry look, even though they just came from water. So feathers tend to have these wax to protect them from water and from moisture. And of course, leaves. If you look at a leaf, most leaves are very waxy to prevent them from completely dehydrating in the sun, right? So beeswax contains the wax myricyl palmitate as a major component. And this right here is that beeswax, which is sometimes used in making candles. And I do enjoy me a candle, you know. Okay, so moving on, like other esters. So remember, wax is an ester. So like the other esters we've seen, waxes are hydrolyzed by water in the presence of acid or base. Remember, the acid or base is acting like a catalyst to reform the parents that made it. And the parents here are carboxylic acid and alcohol. Okay, so let's see right here. This is the ester, right? So remember, when you have the ester, that will be like the sub going back because the teacher came back. You can look at it that way, or you can look at this one here at the beginning of the story where this group is leaving. Bottom line, there's a group leaving and then one replacing the leaving group. That's the bottom line of what's going here. So this group is leaving, LG. In the majors class, is literally called that, the leaving group. I'm like, kudos, chemists, for calling things by what they do. Leaving group, because it literally is leaving. Bye. Okay, and then the water is broken apart into HOH. Remember, OH is the incoming group coming in, okay, to replace the leaving group. So you see right here, the OH came in, and we are reforming the fatty acid and the alcohol that was the starting material. So in the beginning, we saw these two come together to form the ester. Now we're seeing a reverse in the process. Okay, so we're moving on. Again, I have three examples here. I'm only gonna work on one because I really only need to work on one. You can just apply the one thing I do to the other two. Okay, let me move over here. Here's a wax. This is beeswax. I remember when we were kids, like, mind your own beeswax. Well, here's the beeswax we're talking about minding. There it is. Okay, so what is the question here? What hydrolysis products are formed when cetyl myristate is treated with aqueous acid? So this is a hydrolysis process, right? Where you're breaking down the bond, and it has to be this ester bond right here. Okay, you're breaking it down to separate, to reclaim the original alcohol. So remember, with the water, water separates into H and OH. The OH comes over here. Oh, you know what? Let me see. Let me try something, okay? I haven't tried this. Can I cut this? Let me try this. Yeah. I'm trying to be lazy. I'm trying to be smart. Let's see. Oh, come on. Oh, copy? I wanted to cut. It's not the same. It copied the whole structure. That's not what I wanted to do. I wanted to cut. Ah, it's not gonna work. Okay, y'all. I have to draw this out. It only allows me one thing to. I can only copy. Okay, that's okay. The whole time I was doing that, I'm just drawing it out, right? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. They can improve this feature, right? So 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There. Then of course the OH comes in, so now I have OH. Plus on the bottom I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26. Okay, how do I do this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 5, I'm sorry. My drawings are horrible. This looks like something went wrong. Okay. So this is O, and I got the H here, right? So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Mine somehow ended on 26, but it looks weird. Anyway, yeah, the idea is you separate them and then you bring in the missing groups, or the groups that are coming back in. Okay, moving on. We're now talking about triacylglycerol, which is usually called triglycerides, and the doctor will say, you have high triglycerides, or your triglycerides are very good. And then you can be proud of yourself, right? Or it's too high. Stay away from that steak. Stay away from that trans fats. Yeah, such is life, right? Such is life. Anyway, triglycerides. Triglycerides are triesters formed from glycerol and three molecules of fatty acid. Glycerol is that special alcohol that has three OHs, right? Like OOO, right? Glycerol is CH2OH, CH2OH, CH2OH. It has three hydroxides. So when glycerol is reacting with carboxylic acid, it creates three molecules of fat. Okay? So it's a triester versus just having one ester like we saw up here with waxes. Now we have three times the reaction. So below is a generalized block diagram of the triacylglycerol. So here they're showing you what happens, right? A block diagram. So they're showing you this. This is the pattern that shows you what is formed when you have the triacylglycerol or the triester. Okay, so remember, the glycerol that has three OH groups reacts with three fatty acids. Now, the fatty acids can all be alike, they can be different, but you have to have three because all OHs have to be replaced. Glycerol, and here are our three fatty acids 1, 2, 3. Okay. General reaction for the formation of triacylglycerol is we have the following. You see from our fatty acids that this is just the carboxylic acid flipped over. So this bond has to break here, break here, break here. So once again, that becomes the leaving group. Bye. When the leaving group leaves, what comes in the place of the leaving group? Remember, the H separates here, H separates here, H separates here. Because the leaving group that left, the bond broke, it broke between a carbon and a oxygen, right? So the coming group that's coming in, kind of like a prong or a fork, is coming in with its own 3 oxygens right here. Okay, so let me draw this in blue so you can see. These 3 oxygens are right there. So here they are, right here. And they were used to each carbon in the fatty acid. Okay. Oh, so when the leaving groups leave, we know water is formed. How many waters are formed? You got to form 3 waters, because essentially what we're looking at here is 3 times the reaction we saw up there. I'm trying to scroll up, but somehow the iPad is not operating with me. It's not working with me. Okay, let's move on. Triacylglycerols. Oh no, let's use red so I can know where I've written. Triacylglycerols may be composed of 3 identical fatty acid side chains or 2 or 3 different fatty acid side chains. These fatty acids here, they may be exactly alike or they may be different from each other. Okay. The fatty acids may be saturated, meaning they have no double bond. By the time you're done with this class, I think you will have a working understanding of what saturation means in the world of chemistry, or unsaturated, at least 1 double bond. Animal fats and vegetable oils, animal fats and vegetable oils, the most abundant lipids are triacylglycerols with different physical properties, right? Fats from animals tend to be harder and they have a higher melting point. And then fats from lipids tend to be oil from oh my goodness, fats from vegetables tend to be oily and liquidy. Like when you look at the vegetable oil we have in the kitchen, avocado oil, canola oil, which is from something from corn, or vegetable oils, we tend to have vegetable oils versus animal oils. With animals, we tend to have fat, like butter. You can probably tell I'm smiling already. Yeah, butter tastes so good. Ah. As I talk about this class, I'm like, I, this is tempting, man. Butter. Yeah, butter. Anyway, fats have higher melting points. They are solids at room temperature. Fats are derived from fatty acid with very few double bonds. Remember we said earlier, and we're saying it again, the more double bonds you have, the lower the melting point. So greater number of double bonds, lower melting point. That means it's more liquid, right? More double bond, more liquid. Oils have a lower melting point and they are liquids at room temperature. That means that oils have many double bonds, right? And it says here, oils are derived from fatty acids with large number of double bonds. Okay, so solid fats have a relatively high percent of saturated fatty acids. So this is talking about solid fats in general. So if you have a solid fats, that's because there is more saturated fatty acids than you do have unsaturated, the ones with double bond. And so we're told here generally animal fats tend to be solid fats. I don't know what, right now I'm thinking bacon. You know the grease after you cook bacon and then that grease, it kind of, first of all it's melted because the pan is so hot. Then when you leave it after a while it solidifies. Or if you cook a steak, see where I'm going with this? We're talking chemistry. I'm thinking kitchen, right? Food. You cook a steak and it's really fatty marbleized steak, and then the grease. Anyway, yeah. They're talking about that fat right here. That fat is solid. Okay. So now we're told here, okay, why are certain fats solids? So we're seeing here, this fat here is a saturated triacylglycerol. And this is saturated. How do we know that? If you look at all the long chains right here, there is no double bond. If there was a double bond, the way the elements are arranged will be different. If you look at the central atoms here, they're arranged in kind of a chevron pattern, right? Starting with the carboxylic carbon, chevron pattern throughout, zigzag, zigzag, zigzag orientation in the central carbons. We see the same thing here. Zigzag, up, down, up, down, up, down, zigzag orientation. When you have a double bond, if it's a trans double bond, it pattern. You see how closely packed these are? They look like folded clothes. Like I think about folded t-shirts that are folded very neatly, and they're stacked together. That's what this reminds me of. Oh, I can think about pancakes. Oh, I need to stop thinking about food. Anyway, pancakes, stacks of pancakes, right? Packed very close together. I think the clothes thing is better. The food thing is a dangerous territory for me. Okay, liquid oils have a higher percentage of unsaturated fatty acids and are generally vegetable in origin. So that's what they tell you. Liquid oils or liquid fats are better for you than solid fats. Crisco, Crisco may make what's it called? Scones. Y'all don't eat scones a lot. I'm reverting back to my old ways. What's it called? The bread thing. Buns, yeah, those. And they make it all flaky and nice and you know tastes so good, but it's not very good. I mean, it tastes good, but it's not very healthy, right? So in the unsaturated lipid, a cis bond places a kink in the side chain, making it more difficult to pack efficiently in the solid state, thus leading to a lower melting point. Bottom line, if you have a cis bond in your long chain of your fatty acid, that cis bond causes a kink, and that kink makes it impossible for the fatty acid to stack up like pancakes and form solids. This is impossible because they have this arrangement right here. Okay, so they can't pack very tightly. For that reason, you end up having a lower melting point whenever you have a cis bond. Okay, this is showing you what the cis bond does. It introduces a kink to the nonpolar portion of your fatty acid. Okay, so here we're told draw the structure of triacylglycerol that contains three molecules of stearic acid. So we need three molecules of stearic acid and three molecules of oleic acid. Okay, can I do this? I'm going to draw the skeletal version because this looks like a lot. Oh, I forgot. I have it in this mode. Okay, I need to figure out how many carbons I have here. Oh, my eyes are burning. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Hold on a second. Oh, I think it's the allergies. Oh, sorry. My eyes burn. I can't even see what I'm writing. Yeah. Okay. 18. So what I'm going to do here is I'm going to draw my glycerols, right? CH2OH, CH2OH, CH2OH. Now I want to make this smaller because I really need the space, right? So let me move this. Oh, let me move this back in here. Okay. Hold on. Oh my goodness. Such a distraction. Okay. So I need three of these, right? And they have 18. So essentially, to write this here, I'm gonna write this right here, then I'm gonna join them. I'm gonna be lazy, not lazy, sorry, innovative. So I'm gonna do this. OH 1, 2. Hold on. Like this. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So I'm gonna do this. Let me shrink this a little bit. And then copy it and then paste this in my effort to be innovative. Here. Here. Okay, let me erase this and make this slightly bigger to match what I have going on here. I can adapt to that. CH2OH, CH2OH. Okay, so since I'm going to add these to that, all I have to do here is remove the OH. Oops, remove just the OH. Remove the OH. Why won't it leave? Okay, for some reason my OH won't leave. Have I violated some computer function here? Okay, so my OHs won't leave. So what I'm going to do here is, can I remove these OHs? Yeah, those will leave. Okay, these won't leave. So what I'm going to do is, because of my structural issues, I'm going to do it like this. Okay, because essentially that's what happens in the end. Okay, this becomes like that. And this becomes my product from this first one. As you can see, these are stacked together like pancakes, and then that's how they connect to that. Okay, this is going to be interesting. This one here will be very interesting. So I'm going to try to see how I'm going to do this. I'm going to paste this here to have a model to work with. But let me count the number of carbons I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, 18. So I have 18 to work with here. Let me try to draw this out. I'll flip it over so it can look just like this one here. 1, 2. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, 9, 10 is where we have this, right? 11, 12, 13, 14, 15, 16, 17. This is 9, 10. I forgot. Okay, hold on. 2, 3, 4, 5, 6, 7, 8, 9. So I have to go back to this. Oh, it won't allow me. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then double bond. 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, this is 1, right? So once again, this is how this looks. And so I'm going to copy this and paste it 3 times if I can. Can I? It's going to be huge. Okay. Oh, hold on. Yeah, this is going to be, I'm doing my best here, y'all. I'm doing the best I can. Okay, so having done this now, can I erase this? Oh. Why do they allow me to erase one but not the other one? That's so weird. Anyway, so now I'm gonna draw my alcohol there, my glycerol there. And my glycerol is a CH2OH, CH2OH, CH2OH. And of course, you know the OH goes off, right? So the CH2 is the one that bonds with this. Well, come on. Okay, so there's an oxygen here, an oxygen here attaching that to that, and an oxygen here, like that. And of course, this also forms 3 waters, which I forgot the 3 waters up here, plus 3 waters. Okay? Whoa, I made it. That was quite a feat. Okay. Oh, here they want us to draw structures of 2 different triacylglycerols that contain 2 molecules of stearic acid and 1 molecule of palmitic acid. Okay, so for that one, I think once we get past this threshold, the rest of it is just mostly information, right? I don't know. We'll see. I'm trying to just guesstimate what's coming next. We'll see. I was trying to look over the notes to see what's coming next. Okay, so for this one here, Let me see if, since I saw how I can do this, let me see if I can make this go faster. Copy, paste, 1, paste, 2, paste, 3. Oh, let me move this further down. Paste. No, come on. Okay. Let me copy this. There's 2 stearic, right? 2 stearic and 1 palmitic acid. So let me copy this. Paste here. And then copy this. Paste it in the middle. Okay. Hey, this might work. Great. So I know my carboxylic acids have to be facing, the carboxylic end has to be facing the glycerol end. So I'm going to draw my glycerol here. Actually, let me draw it differently. I'll just say CH2 dash O, right? It's going to be O dash CH2 O dash CH2 there plus 3 waters. See how much quicker that went? Here, my 2 stearic acids, my 1 palmitic acid, and bam, that works. See, I have some ideas that, oh, come on. We were in a roll here. What happened? Move. Can I move this over? What happened that it moved? How did it move? I didn't even move it. Cut. Let's see. Can I cut this? Okay. Can I paste? I don't know why it moved, but here, stay there. Okay. Let's do the same thing over here. Right? CH2 dash O dash CH2 dash O dash CH2 dash O dash, connect these and voila. Okay. Don't forget your 3 waters. This is our products, right? Okay. Now we're moving on. We're talking about fats. Fats are used to build cell membranes, insulate the body, store energy for later use. Fats are different from glycogen or glucose because glucose is usually a readily available source of energy. So that would be, when I was learning this, I remember thinking about checking account versus savings account. When you want a quick way to access your money, checking account is the best way. There aren't long processes and stuff like that. Well, things are kind of different now. This is back in the days before you had all this online banking situation, right? You can easily now get money from your savings account, but maybe how about a long investment account? Okay, so and fats are invested, so to say, energy, so you can access it, but you have to go through more steps to access it. Okay, it's not as simple and quick as glycogen. So remember, glucose, any excess glucose gets stored in your body as glycogen. So fats are used in your body to store energy for later use. It is recommended that no more than 20 to 35% of a person's caloric intake on a daily basis comes from lipids. It is recommended. It's not a law. They can't come after you just in case you had an extra fry. I had some fries for lunch today. Tasted good. Okay. A high intake. I do eat healthy, actually. I do eat healthy. Yeah. I normally eat healthy. A high intake of saturated triacylglycerols is linked to heart disease. So when you eat a lot of saturated fats, right, this is linked to heart disease, and this is serious. Saturated fats stimulate cholesterol synthesis, and they can lead to cholesterol plaques. Remember, because of the way they pack, building up inside the arteries, and we're told here this can result in high blood pressure, heart attack, and even stroke. Okay. Is this the person driving in the street? Yo, we're on the 10th floor, and I'm hearing somebody like they're on the same level as we are. That must be very, very loud speakers. Hold on. This is Friday night, y'all. People are out there living their best life. Meanwhile, I'm here doing this lecture. That's okay. This has to be done. Okay, where were we? Unsaturated fats are a lot better for you. They lower the risk of heart disease. Remember, these are the good fats we're talking about. What were we talking about? Good fats. Olive oil, avocados. Talking about which? That sounds good right about now too. These help to decrease the level of cholesterol in the blood. Triglycerols form from omega-3 fatty acids such as fish oil are very helpful in lowering the risk of a heart attack. There was a time where I was an avid taker of, omega-3 pills and stuff like that. I've gotten lazy to where I don't take it, but I should get back into that. I try to eat a lot of not fishes, but fish too, because it is healthy for you. However, if the double bond of the unsaturated triacylglycerol is trans, the benefit is lost. So if the beneficial effect that we get from the unsaturated fatty acid is lost, if that fatty acid is classified as trans, that's why a lot of grocery store foods advertise no trans fats. Okay, have I actually taken the food out of that pack and tested it to make sure there's really no trans fats? No, you just kind of trust them and then you eat it and you hope for the best. Trans fats, which are primarily synthesized instead of naturally occurring, act like saturated fatty acids and therefore they increase cholesterol levels in your blood. Okay? So here's an example. You see how this part here, these are all saturated, there's no double bonds. And you see how they have that stacked look, like the stacked pancakes? And this right here is unsaturated. You almost missed it, huh? Because there is a double bond here, but this is trans fats. What makes trans fats bad is the fact that the bond orientation makes the trans fat chain just like the saturated fat chain. It can all stack together very closely, which can easily cause your body to form plaques, making this a solid at room temperature, and it can form plaque, and plaque is not good. Okay, so moving on, triacylglycerols are hydrolyzed with water in the presence of acid or base or enzymes. So now that we've made the triacylglycerol, we're now breaking apart the ester bonds to get the reactants, right? You would do this 3 times. So you would need 3 molecules of water. Each molecule of water is replenishing what was lost from the glycerol and then the fatty acid. So we're breaking this part right here, breaking this here, breaking this here, and H will come in here, here, and here, and OH will come in on the other side here, here, and here. So you can see how the OHs, they got lazy, and they just wrote 3. You get it. Look at that 3 times. The OH came from the water, so imagine the water H2O being H and OH, right? These OHs from here, and then of course the H's go over here, and here, and here. Okay, to remake the glycerol. Okay, humans store energy as triacylglycerol in adipose cells below the surface of the skin. So you know how I love to work out and I do work out. Sometimes I watch workout videos and then I heard things like skinny fat and I'm like, what in the world is that? And so sometimes some people can be skinny fat. They look skinny, but they have a lot of fat. And so if you're going to have a lot of fat, I hear from people who are workout gurus and health fanatics that it's better for you to have the adipose cells, all the extra fat underneath your skin. That's called the adipose fat, right? Versus having the visceral fat, which is around your internal organs. This is the bad one. This is the one that causes all the illnesses and stuff. Okay? So if you have adipose tissue underneath the skin, that's like, okay, no big deal. But when you have it in your internal organs and you have visceral fats, that's the problem. So yeah, the skin, underneath the skin, underneath the breast area. I mean, all fats are bad, but between the bad fats, the ones that are worse are the ones that are in the visceral. This is the one in your stomach area. Once again, the ones around your organs. It's difficult to work those out because they're not underneath your skin. Those usually controlled by your diet. Your diet does a better job at shrinking the fat cells around your organs. Okay. So apparently we have a fixed number of adipose cells in our body. The number of adipose cells in our body is constant. Oh, that was the term I was looking for. The fat underneath your skin is subcutaneous. I keep forgetting the biology term, subcutaneous underneath the skin, right? Versus visceral around your organs or in the middle of your body, your waistline. Okay. Anyway, the number of adipose cells is constant. You have a fixed number of fat cells. So weight gain or weight loss is caused by swelling or shrinking fat cells. Okay, so now I've read this a lot. I've read this a lot. Then I was watching some videos on YouTube. Y'all see, I watch a lot of videos on YouTube about liposuction. And I was thinking about it. So, and I've tried to research some of this on even government websites, NIH. I even checked, y'all, to see if we have a fixed number of cells. If you get a lipo, okay, which people usually get lipo for cosmetic reasons, but I'm thinking like a scientist, okay, focus here as a scientist. If fat cells around your internal organs causes a lot of problems, all those illnesses, right? High blood pressure can lead to a stroke, all these other things. Can having a lipo help you out? Because technically liposuction involves destroying and removing adipose cells. I wasn't trying to look into this to look cute, right? But guess what? Somebody published a research paper. Yes, you heard me. Somebody actually published a paper where they said that they did examine this possibility. So somebody out there before me thought about this, and they actually went ahead and did their research, like a research work, and noticed that no, cosmetic lipo does not help you with the internal organ fat, because cosmetic lipo removes visceral fat to make the body appear better. They don't go inside and do major surgery to remove the fat around your internal organs. They said that there's a slight change, but it's not significant enough for doctors to recommend this. I thought that was very interesting. Yeah, they don't recommend that to help you with things like high blood pressure. Okay. So just in case you're wondering, there you can look at the NIH website. They do have the research on there. I don't have the reference to that, but I just thought it was interesting. Anyway, so the other question is, does liposuction help? Now, in no way am I endorsing this. We're talking about this academically. Does it help? Theoretically, even though you liposuction does reduce the number of fat cells, if the fat cells can swell, you can theoretically gain weight again by the few adipose cells that remain getting bigger. Because somehow, even though the surgery was done, there is no change in lifestyle, right? So liposuction isn't an easier way for weight loss. I think the better thing is to work out and watch your diet. Watching your diet, number one, working out, number two, because diet is like 80%, right? That's what they say, right? So once again, I checked this with research. Okay, I just had some questions and I did my research and I was like, okay, fine, I'll work out. I will work out and eat healthy, right? Okay, so to metabolize triglycerols for energy, the esters are hydrolyzed by an enzyme called lipases. Now we're talking about this hydrolysis process happening inside your body. So in your body, the catalyst we have in our sulfuric acid, we have actual enzymes that behave as biological catalysts. So lipase will be the enzyme that breaks down lipids. And lipids is actually a very interesting topic to me because once I left school and I was watching TV one evening, they were selling this pill. And TV talks about a lot of things that we cover in this class. And they're like, we're selling this liposine. I'm like, mm-mm. Liposine? That sounds like a lipase. Oh, it's this enzyme that helps your body break down fats. I'm like, well, the idea sounds good, but once again, I want to know the science. I want to see how is this liposine or whatever it is that you guys are naming, how does it mimic the real lipase that you naturally have in your body? What are the side effects? Because everything you put in your body has a side effect, right? And here I am today going off on all these soapboxes. Yo, anyway, yeah, so you just kind of need to be careful about these things that they advertise. I'm usually curious about uh, actually getting one of those pills and analyzing its contents in the lab. We do have a machine that can analyze the contents of different things. Have I had time to do that? No, I've been so busy teaching, but someday, I would like to do that. Get those random pills that promise quick results in whatever, and really analyze to see if those pills have what they say they have, and then what's the side effects of taking those pills, things like that. Anyway, complete metabolism of triacylglycerol yields carbon dioxide, water. So when we burn off fat, we actually exhale it, right? I remember this coworker who used to ask, how do you think we get rid of fats? By metabolizing it and exhaling it. Okay. So sometimes I think about when you're having like not really a panic attack, but if you're doing something that increases your breathing, that's actually helping metabolism, right? It helps metabolism. That's why they say that if you want to do cardio to really lose weight, don't do the kind of cardio where you can walk and still talk. You need to be a little bit out of breath. You need to get your heart rate up, because when you're breathing more and breathing faster, that actually helps to boost metabolism. Because the goal is, remember, when you're breaking this down, ultimately, you're producing carbon dioxide and water. The goal is the more of this CO2 you bring out, the more fat you break down, right? It's interesting, y'all. Very interesting. Draw the structure of a triacylglycerol that fits each of the following descriptions, or that fits each description. A saturated triacylglycerol formed from 3 12-carbon fatty acids. Okay. An unsaturated triacylglycerol that contains 3 cis-bonded. Are you kidding me? Okay, you know what, guys? I did this before, right? So I think I can actually just copy that from before to here. I should be able to do that. Okay. A trans triacylglycerol that contains a trans double bond in each hydrocarbon chain. I won't be lazy, y'all. I won't be lazy. Okay, so for my first one, I'm going to just draw one and then fill in the rest. Wait, why won't this go away? Okay. Wait, did I do something? Oh, I was about to say, what did I do? Okay, let me come back to this. I'll erase this right here. Okay, so I'm doing this first one right here. 12 carbon fatty acid. Okay, the first carbon is my carboxylic carbon. This is my first one. I keep forgetting. I'm gonna do the skeletal one because that's the easiest. And now I'm just like, okay, that's my first one. Second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10, 11, 12. Okay, and I'm gonna draw this 3 times. Drawing is the same thing as copying and pasting right now. Copy, paste. Move over. Why is this? Hold on. Is something going? Maybe I'm moving too fast for it. There. Okay. Then copy, paste. Somehow I feel like it's not responding to the pencil, and it's not responding to my touch, and it's just okay. Okay, as usual, you know that you have your glycerol here. So what I'm going to do to make this go a little faster and then shorten the video, I'm going to draw on top of this, right? This allows me for the first one. The second one, I have to draw a whole different structure from that. I'm going to do the first one first. That's done. Then this third one, C, trans triacylglycerol that contains a trans bond. Okay, trans. All I have to do here is just put this trans here, trans here, trans there. So that was the first one. Now this is the third one. So now I have to do the second one. So here we have to have 3 cis double bonds. Wow. Cis double bonds. I'll make it right in the middle over here. 1, 2, 3, 4. I'll make this shorter, y'all. 1, 2, 3, 4, 5, 6. I should make this a little bit high. Oops, great. 1, 2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to draw this 3 times. Copy, paste. Oh, this is responding a little better. Maybe I'm slowing down a little bit more. Maybe I was moving too fast. I don't know. And then paste here. Come on, paste. Okay, hold on. Let me see if I can move this down. There. Man, this is going to be, okay, yeah, it's going to be humongous. Let me see if I can, okay, so here we have our CH2, O, CH2, O, CH2, O. Then connect these, and there we have our cis fatty acids, our triacyl fatty acids, where the fatty acids are cis, okay? So remember, this first one was both the 12 carbon fatty acid, and I converted it to the trans fatty acid. This one, as you can see here, is the cis. And I have to even draw them apart and draw it larger so I can make room for that kink, right? So hopefully you can see that. Okay. With this one here, it says, draw the products formed from the hydrolysis of each of these. What I'm going to do here, I'm going to just draw one, then we'll move on. Okay. So I'm just going to work on this one here, the one on the left. They keep making these weird updates that makes them the app act differently. Okay, so once again, draw the product. So when I add 3 waters here, what I get, and it can be 3 waters and then maybe lipase, the enzyme. What I get is CH2OH, 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 like that, the glycerol, right? And then for the carboxylic acid, the fatty acid, I have this OH, double bond, OH, double bond, OH. And I have the rest of the molecule, CH2, 12 times CH3, CH2, 12 times CH3, CH2, 12 times CH3. Okay. Yeah, that's it. These are the fatty acid and then glycerol. Okay. Triacyl glycerol. Okay. Moving on. Sorry guys, I'm getting tired. Okay, so we're moving on to soap synthesis. And so we're talking about fats, right? And I think I mentioned earlier that soaps are essentially fats. So soaps are metal salts of fatty acid prepared by base hydrolysis. So you have a fatty acid where this used to be a hydrogen, and then the hydrogen was replaced with a sodium ion, and now we have a salt. So, and if I've known some people who are soap makers, we made soap in the lab before, and then we tested the pH and it was too basic, and I was like, we're not going to use that because that soap was so caustic. It would strip the oils from your skin, and then you look ashy. If that's the goal, go for it. If that's not the goal, then you want to add some oils and make the soap and make it a little less basic so that it's more moisturizing and not stripping off the natural oils. Okay. So here we have salt of the fatty acid. So remember that this end, once again, is the polar end, and then we have the non-polar end, the oily end. We talked about this before. We're talking about it yet again, that the design of soap is to help soap, well, at least the soap that we use, is to help soap use the non-polar tail to dissolve dirt, and then it just sits on your body waiting for you to wash it off. Once you run water on your body, the polar end of the soap interacts with the water, and so the soap washes off, taking dirt with it. It's like, yeah, it was just there to pick up dirt, and on its way out, it gets dissolved in the water and then leaves, right? So here they're showing you once again how the soap is made. Soap can be made from esters. So we see here where this group leaves, right? And when it leaves, guess what it gets? It gets the H from the base. This H comes from the base. So this, the way this breaks apart, it breaks apart. It depends. I've seen different books write it differently. Some books write it as though the NaO goes together and then H goes by itself. Some people do it that way. Some people just break it up in the middle right here, whichever. Yeah. So I've seen two different books write it differently and argue for both points. So the bottom line is you have the H's here, and then now you see this right here. So I mean, we could just stick with something simple. Since we saw this before as Na and OH, we can go with that. But for that to work out, we essentially have to have, you know, Na coming here. So in this case here, then the bond breaks. To stick with that, the bond breaks over here, right? And that would make more sense. But if the bond breaks over here, then the O and A has to come in together. You get what I'm saying? Right. Scientists are trying to make sense of something that's already happening, so they have reaction mechanism, which are hypotheses. I mean, they're proven based on experiments, which proves one mechanism is stronger than the other to explain what's already happening. Okay. Ultimately, we get our glycerol right here, and these are soap molecules. Soap. So you know how Bath and Body Works has all these flavored soaps and stuff like that? Yeah, this, at some point somewhere in their lab, there is someone who is making soap with all the oils and all the flavors and all the smells and stuff. But at the bottom level, you have soap. So the non-polar tails dissolve grease and oil. Then the polar head makes the soap soluble in water so it can wash off your body. Okay, what is the composition? That's the question we're looking at here. What is the composition of the soap formed by basic hydrolysis of each of the following? Triacylglycerol. Wait, didn't we do this before? But we did it with the water. Okay, so this time I'm gonna pick this one here since last time I used that molecule. Because I'm like, this looks very familiar, doesn't it? It does. It's the same one. At some point, I feel like even the authors get tired of coming up with new formulas. They're like, well, we get the idea, just show the process using the same formula I showed you before. Okay, so what I'm going to do is I'm going to make this simple and say that this bond, oh, no. I'm going to make this simple. Because back here, though, they showed this bond here. Make it simple. And show it breaking right here. And if that's the case, then the sodium and then the hydroxide are separating like that. And so if you have that going on, then let me see if can I draw this over here? Can I make this smaller? Hold on a second, let me make this smaller. Can I make this smaller? Okay, this is not working. I'm going to give up with that. I'm going to move on with this one right here. Let me make my sodium hydroxide smaller here. Sodium separates from hydroxide, and then let me draw this out. The first one will have carbonyl, oxygen, carbonyl, oxygen, carbonyl, running out of room, not yet, carbonyl, oxygen, negative, 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 sodium is positive, because this is a salt, right? And then the rest of the molecule, can I squeeze this in there? CH2, we got 12 of these, and then CH3. Then we got CH2, 7 of these, CH, double bond, CH, CH2, 5 of these, CH3. Man, barely. CH2, 7, CH, double bond, CH, CH2, 7, CH3. Barely, but you get the idea, right? And then on the other side, we have plus 3 waters, right? This is our soap. So when we're in lab and we're making this, we made a lot of soap because you can see how each one of these triacylglycerols produces 3 times the amount of soap. Okay, now we're done with soap and we're moving on to your body. Phospholipids. So phospholipids are lipids that contain phosphorus atom, P. Okay. Phospholipids are an important component of your cell membrane. So phosphoacylglycerols are the most common phospholipids, and they are a principal component of most cell membranes in the body, cell membranes in animals, okay, and plants. So essentially here we're told the cell membrane is the skin of the cell. It's kind of a paraphrase, very weak way of presenting that. And so the chemical component of phospholipids is you have the glycerol right here, triacylglycerol, and then you have one of the fatty acids is replaced by phosphate and an alcohol. Okay? So structurally, phosphoacylglycerols or phospholipids resemble a triacylglycerol, right? You see that, right? If we had replaced this right here with a fatty acid, we would essentially have a triacylglycerol. So that's why fats are an important part of your body and your diet. You can't, if you go on a completely no fat diet, it's not healthy for you because fats are essentially part of the skin of your cell, the cell membrane. So you have to have it in your diet. It just can't be your main diet. Okay? Can't be the main portion of your diet. Okay, structurally they resemble triacylglycerol, except that the third fatty acid has been replaced with a phosphodiester bonded to an alcohol. So you have a phosphate using a phosphodiester bond, and this phosphate is bonded to an alcohol. There are 2 main types of phosphoracylglycerols that differ in the identity of the R groups in the phosphodiester. So this is showing the general form of the phospholipid, and we're told that the R group right here, apparently there are 2 phospholipids, and the R groups is what makes them different. So let's go over here and see what they look like. You have one called cephalin. This is one type of phospholipid or phosphoracylglycerol called cephalin. And with the cephalin, you have, of course, your glycerol group right here. You have your fatty acid, glycerol, fatty acid, check. And then in the place of the third fatty acid, we have the phosphate. You can see that here. Phosphate. And then you have this amine group, right? It's more like an amino group, but anyway, amine group right here. You can see that. And then this, oh, by the way, this right here is a primary amine, and you can see that. And then right here we have the other one that's called lecithin. Once again, we have the glycerol. You can see that right here, glycerol, if I can spell correctly. We have the fatty acid. We have the phosphate here. And then we have this, looks like a tertiary amine, right? No, this is not tertiary. Take it back. Quaternary amine. Because this nitrogen is attached to 3 CH3s on one end, right? These are 3. And then it's attached to a carbon on the other end. That's 4 groups. Over here, let's see. This nitrogen is considered primary because it's attached to 3 hydrogens, but it's only attached to 1 carbon. The definition of primary, secondary, and tertiary ties to how many nitrogen boils down to how many carbons the nitrogen is attached to. So this is technically primary, and this is quaternary, 4 degrees, right? Because there's 4 NC bonds, 1, 2, 3, 4. Okay. Anyway, where was I? So essentially we have cephalin and lecithin, okay? Draw the structure of 2 different cephalins containing oleic acid and palmitic acid as fatty acid side chains. Okay, so I don't know why the cut feature is not working here. It should work. Oh no, you see, it's not even copying the right thing. Okay, what I'm gonna do here, guys, I'm just gonna modify the structure here. Okay, we have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so what I'm gonna do, let me add a page here. Yeah, I'm getting a little fatigue here. Yesterday I started fatigue. Today I'm getting fatigue. At least it's better than yesterday when I was already tired before I showed up. Hold on. So let me make sure we're drawing this on cephalins, right? So they want us to use one of each fatty acid, oleic and that one. Okay, so we have what, 18? This is the first one. First, second, third, fourth, fifth, sixth. First, second, third, fourth, fifth, sixth. This is 6. 7, 8, 9, double bond. 10, 11. 9 and 10 have a double bond, right? 11, 12, 13, 14, 15, 16, 17, 18. This is 18. So that's good. The next one here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. Okay, this is 1, 2, 3, 4, 5, 6, 7. This is 7. 8, 9, 10, 11, 12, 13, 14, 15, 16. This is 16. Okay, this is it. Okay, I managed to put them both in there. Second one's a little bit squeezed, but you get the idea. Number of carbons are correct. Was that it? Okay. Oh, 2 different cephalins? Come on. Okay, I can do this, guys. I don't have to be that lazy. I'll do the first one, copy this. Paste here. This may not work. You know what? This is not gonna work. Let me undo this. Okay, let me go back. I have my ideas, but I'm limited in what the app can do because I'm okay. Here's the thing, I'm using the free version, so I can't complain, right? I'm like, oh, I like free things, and then when it's not doing certain things, I'm frustrated. So I can't complain too much. So I'm sitting here thinking, why can't it do A, B, C, D, and E? Yeah, well, you don't want to pay for it, right? Ah, I call myself out, y'all. Come on. See, sometimes it allows me to copy part of the molecule, but sometimes it doesn't. So my goal for this is to flip the R groups. Hopefully you see what I'm doing, right? I'm trying to flip them. Okay. So this would be CH2-O-C double bond O, right? CH2-O-C double bond O. And the last one here is CH2-O-P. This is the phosphate group right here. Double bond O, O, sorry, this is one. Let me go back. O minus O dash CH2 CH2 NH3. This is positive. Okay, I just flipped this over to get my second structure. This is my second structure. This is my first structure right here. Okay. Okay, let's keep going. Classify each lipid as a triacylglycerol, cephalin, or lecithin. Okay, so let's see. This is triacylglycerol. Because you see there's no phosphate here, no phosphate. This one here has the phosphate, but it has your primary amine. So this would be what? Cephalin, right? We said back here, cephalin had a primary amine. Okay. Doing good. Now we're moving back to the story. So we kind of detoured a little bit back to the story of the phospholipid in the body. The two fatty acid side chains form two nonpolar tails. So after doing all this, they're telling you that these side chains here, remember these are fatty acid, if I can say this correctly, this is the phosphate group. So if you take this phosphate group here and you kind of roll it up to put it down here, then these two form a chain. So it's not chain, sorry, they form a tail. So imagine, right, you roll this up into a ball right here. These two form a tail. So from this structure, we get that structure. The polar head here includes the glycerol backbone plus the phosphate. Okay, this is, if you ask chemistry to give an account of what the phospholipid looks like, this is the chemistry version. This is the molecular version, right? Giving you the elements and how they're bonded together in the chemical formula. If you ask a biologist to give the same account, this is the biology version. Okay, that same molecule, chemistry version, biology version. So we're told the two fatty acid side chains form two nonpolar tails that lie parallel to each other. The phosphodiester end of the molecule is charged as the polar head. So the shove it to or scooch it to the left with the glycerol head right here. And then those two fatty acids become the nonpolar tails. Anyway, so moving on, talking about the structure of the cell membrane. The basic unit living organism is a cell. The cell membrane surrounds the cell cytoplasm, the aqueous medium inside the cell. The cell membrane acts like a barrier to stop the passage of ions and molecules in or out of the cell. So the cell membrane is kind of like our skin, and our skin is porous, right? But it allows certain things to go in and certain things can't go in. We know our skin has pores. The cell membrane allows certain things to go in and certain things can't go in. The other job of the membrane is to allow nutrients in and waste out. In this way, the cell membrane is selectively permeable. I remember I had to learn this word in biology. They didn't say selective, they said semi-permeable. So certain things can go in, certain things can't go in, certain things can go out, certain things can't go out. So you don't want your cell leaking nutrients because you need nutrients, right? Phospholipids, the major component of the cell membrane, contains a hydrophilic polar head and two hydrophilic nonpolar tails. This right here is essentially the phospholipid, okay? And so you have the polar head, the one that likes water, loves some water. And then nonpolar tails hates or fears water. So remember, scientists try to what's that word? Anthropomorphize? I can't say that word correctly. They try to humanize these elements. Elements haven't sat there and told you they don't like it. They just move away, right? But we interpret that as hating water. So if you put this phospholipid in the water, the nonpolar tails will move away from the water, and then the polar end will interact with the water, almost be drawn to it. Anthropomorphize. Yeah. I had to say it. Anyway, so this is showing you how these phospholipids are arranged in the cell in our bodies. And remember, our cells are kind of surrounded by blood, and blood is aqueous. Okay, so you can say essentially these phospholipid bilayers are essentially in water. So when they're mixed in water or blood, right, in our body, they assemble themselves in a lipid bilayer so that the portion of the molecule that loves water faces water. So it's kind of like when I was looking at this as a student, I was like, this is kind of like an army formation, right? Where you have the soldiers facing outward and they have the shield in front of them facing outward, but then their back is facing the back of a soldier behind them, right? So your back is being, when people say I got your back, somebody behind you is not really watching your back, but their back is facing your back. So by them being behind you, they're kind of watching what's going on behind you. I guess that's what watching your back means. I don't really know these things, but yeah. So these molecules line up and layer themselves in a bilipid layer so that the parts of the molecules that hate water are spared from interacting with water. And the parts that love water, this is what water loving, interact with water. And then this portion here is water hating. So you can see the hydrophobic interior. When you get to the interior of the cell membrane, you encounter a lot of hating of water. But on the surface of the cell membrane, there is love of water. Okay, so this is showing you the cell membrane, kind of zooming out and telling you it's not as simple as having a bilayer. There's a lot of stuff in there. So remember, I used to actually like going over this in biology. It's a lot of strategy. So think about the function of your cell membrane. There's a lot of stuff that goes through our cell membranes, right? On one hand, some things have to go through the cell membrane, some things can't go through. Here you see we have some cholesterol. So a healthy amount of cholesterol is important for your cell membrane. It's important for your own cell membranes and your brain cell membranes. These are all important for that. We have some carbohydrates here. So yeah, carbohydrates are important for your body, y'all. You see that right here? Cholesterol and carbohydrates. All they're saying is moderate the amount, not stop eating it. So occasionally I eat me some carbs and I'm like, you know what? My body needs this occasionally, right? Let me be honest. Every morning I eat a slice of bread. So yeah, that's like every morning I eat carbs. Yeah, not just occasionally. I just don't eat it too much, right? Okay, so here, what if things have to pass through your body? You have carbohydrates here. We have chemicals that allow one cell to signal the other. There's so much going on here. You have means for vesicles. Now I'm trying to teach biology, right? Biology is not my thing, but chemical neurotransmitters to travel from one cell to another. There's so much going on between cells, right? And so here you have this integral protein. It's called integral because it goes from one end all the way to the other. So this will be like a bridge, right? And the integral protein is a channel, like a bridge, like a tunnel, not a bridge. This is like a tunnel that allows polar things to go through. If you have something polar, it can go through this tunnel right here. Okay, so let's keep reading on and we'll see. Proteins and cholesterol molecules are embedded throughout the lipid bilayer. Peripheral proteins are embedded within the membrane and extend outwardly. They extend outward on one side only. So you have peripheral protein. Peripheral means like outer or on the surface. Remember that peripheral atoms? Outer, right? And then you have integral. Integral is kind of like part of, within. These extend throughout the entire bilayer. Sometimes carbohydrates are attached to the exterior of the cell, forming glycolipids and glycoproteins. Okay. Sometimes they're involved in cell signaling and cell identity. So it gets a little bit more complicated, right? To know the actual story of what's going on here, take a biology class. Okay, small molecules such as oxygen, as we're breathing right now, and carbon dioxide can diffuse through the cell membrane, traveling from higher to lower concentration. But wait, let's think about it for a moment though. Oxygen. Let's talk about the lowest structure here. This is nonpolar. Carbon dioxide. Also nonpolar. We'll talk about that later on. Larger polar molecules. So I guess I should talk about it right now since we're here. But notice that oxygen is nonpolar, carbon dioxide is nonpolar. Since these are small molecules and they're both nonpolar, they can easily travel through the membrane. Because remember, while the surface of the membrane is polar, the interior of the membrane is nonpolar. So they can travel through here without hindrance from the interior of the cell membrane because their nature matches the interior. So they can easily diffuse through the cell membrane because the inside of the cell membrane is nonpolar like them. But if you have a large polar molecule that needs to move through the membrane, it needs facilitated transport. It needs something to help it out. Because remember, number one, it's a large molecule. It can't just travel through here and notice. What? No. And it's large and it's polar. How does something that's polar get to a non-polar region? Not going to happen. So this is why you need facilitated. Facilitated means to help you out. You need some kind of help like a Uber, not really an Uber, but facilitated transport to cross efficiently. So to give you an example here, the facilitated transport is essentially the integral protein channel, the one that's the tunnel. When you have ions like chloride ions is large, okay? Bicarbonate ions, also large. When through the cell membrane, and they are charged ionic slash polar, right? They need the help of the integral protein channels because the protein channels essentially provides a means for things that are ionic or polar to travel through without them having to interact with the nonpolar region. Remember, when these chemicals have different natures, they don't want to deal with each other. Polar doesn't want to deal with nonpolar and vice versa. It's not personal, it's chemical. Other ions such as sodium, potassium, and calcium ion, these tend to move against the concentration gradient, meaning they go from a low concentration to a high concentration. So for that, you have to actually kind of force them through. So they say this is active transport. So here we're seeing different transports across the cell membrane, okay? First one here, this would be like your CO2, O2, and I'm so glad. I mean, this isn't a personal thing, but it's good that CO2 and O2 travel through your cell membrane easily, right? Without a lot of help, without any help at all, right? Simple diffusion. Then you have the facilitated transport, such as the chloride and the bicarbonate ion. They need help, and the help they get here is they have that tunnel, the integral membrane protein, and then they travel from a high concentration to a low concentration, which happens naturally. Now, when it comes to the ions, the potassium ions, the sodium ions, these ions are very important in the functioning of your cell. And then, of course, you also have calcium ions for your bones. These are so important. I was having some cramp issues with my legs. It wasn't even over working out recently. So I'm like, okay, I recognize the importance of these ions. I took some Gatorade. Yeah. Anyway, I recognize the importance of these ions now as I'm talking about them right now. I'm like, I'm grateful things work, right? So these tend to move against the concentration gradient, meaning they're going from a low concentration to a high concentration. Imagine like you trying to go up a hill from a low altitude to a high altitude. You need to apply more energy or exert more effort or just try harder going up a hill. This one here, you're going from a high concentration to a low concentration. So you're going with the concentration gradient. So here you don't need any energy except for you need protection against the nonpolar region. So here there's two things that happen with the potassium ion, sodium ion, and calcium ion. First of all, there's a channel to protect these ions from the nonpolar region. Very good. From the integral membrane protein, number one. Number two, they need to be forced through here. So it's called active transport, where energy is needed to force these ions through that channel. Okay? Moving on, why don't ions readily diffuse through the interior of the cell membrane? I think I've already mentioned that so many times. The interior is non-polar. Therefore, only non-polar, small chemicals, and I should say small chemicals, can diffuse through, kind of like just slide through. No, right? Just bubble through. They have to be non-polar, and then they have to be small. Okay. Would you expect a triacylglycerol to be contained in the interior of a lipoprotein particle or on the surface of the phospholipid? Oh, we haven't even talked about lipoprotein yet. Excuse me. Yeah, a triacylglycerol. This is, okay. So even though we haven't talked about this is kind of a trick question, right? The question here is just asking you, is a triacylglycerol, because remember, things that are in the interior of the phospholipid, we know we have nonpolar environment, right? So even though we haven't talked about the lipoprotein that much, the question here is, if something is going to be in the interior of a phospholipid, it has to be nonpolar, like the interior of the phospholipid itself, right? So is triacylglycerol polar or nonpolar? We've seen that based on all those R molecules, for the most part, is nonpolar, right? It's fatty, it's nonpolar. The nonpolar region dominates over the polar part, so it should be in the middle, right? Okay, that was a tricky question. Oh, I think I can finish this. Okay, moving on. Talking about steroids. Steroids are a group of lipids whose carbon skeletons have several cyclic alkanes fused together. And steroids tend to have this A, B, C, D ring. There's so many different kinds of steroids, but you recognize them by them having this A, B, C, D arrangement of the cyclic alkanes. Okay, this was steroid, right? We're now moving on to cholesterol. Hey, don't these look alike? Steroids, cholesterol? They're very similar. Cholesterol, the most prominent steroid, is synthesized in the liver and found in almost all body tissues. Okay? It is obtained in the diet from many sources, including meat, cheese, butter, and eggs. Why is cholesterol classified as a lipid? Well, we talked about cholesterol being one of those non-hydrolyzable lipids, right? So why is it classified as a lipid? It's non-hydrolyzable. So when you see right here, it has so many carbon-hydrogen bonds. And these are those non-hydrolyzable lipids where you can't just add water to them and expect them to kind of break apart, right? Moving on. We're talking about health right here. So cholesterol, the most prominent steroid. Elevated levels of cholesterol in the bloodstream leads to coronary artery disease, heart attacks, things like that. In the it is transported through the bloodstream by lipoproteins. Remember how we mentioned lipoproteins? Now we're seeing lipoprotein. Lipoprotein is like a purse, but it's not really a purse. It's round, and it encapsulates whatever it is transporting. Okay, so in this case, cholesterol is transported by lipoprotein aggregates of phospholipids and proteins. Low density lipoproteins, LDL. Remember when you have that blood test, your doctor tells you about your LDL? So the LDLs, low density lipoproteins, transport cholesterol from the liver to the tissues. The HDLs, that's why they monitor these two numbers, transport cholesterol from the tissues back to the liver. Okay? So this is the number that they want you to track all the time. The question is, which of these do you have to monitor? Both of them, of course. But when is it okay? When one of these is high, you have a problem, right? And which one is that? They're going to tell us in a little bit. This is the lipoprotein. So you see, to me, I see it as a vesicle, like an object with which transports whatever is holding inside. So here we have cholesterol in here. Some of the cholesterol is embedded in the actual, I want to call it vehicle, but it's more like a vesicle. Yeah, a container that holds all this cholesterol and transport it throughout the body, right? And so LDLs deposit cholesterol on the walls of arteries when they carry more than is needed to form cell membranes. So LDLs, once again, are transport vesicles to take the cholesterol to help build the cell membrane. When they carry too much, when there's too many of these LDLs coming in, it ends up on the wrong place, the walls of the arteries. So if you have too many of these LDLs, that's not a good thing, right? This forms plaque, which restricts blood flow. That's LDL cholesterol. It's called the bad cholesterol. It's bad just because if you have too much of it, that means too much of it is bringing to your arteries. You want it, but not in your arteries, right? If you have few of the amount of the LDLs, that means that doing the job, you don't have all these extra LDLs taking cholesterol to your arteries. HDLs reduce the level of cholesterol in the blood by bringing excess back to the liver. So as we are reading this, because this is something that I try to remember, but then I forget. HDLs, because I'm thinking high should be bad and low should be good. No, it's about the function, right? HDLs take any extra cholesterol to the liver where it gets dealt with, right? So for that reason, HDL is a good cholesterol. So you want to have many of these HDLs taking the cholesterol away from your arteries, and you want to have less of this. So the goal is to have less of this and many of this. Yeah. Recommended levels of HDL are greater than 40 milligrams per deciliter of blood, and then LDL is less than 100 milligrams per deciliter. Total serum cholesterol is less than 200 milligrams per deciliter of blood. Okay, so here, identify functional groups in these two. These are statins, which are cholesterol controlling medications. So we're going to go through this real quick. I can see some benzene rings here. Benzene / aromatic. Real quick. I see an alkyl halide, right? I see amine. I see an amide right there. I see your carboxylic acid right there. So let me try to highlight this, these, this. Oh, I see an alkene. I see alcohol. Man, see why these drugs have so many side effects? All those functional group in one drug and you put it in your body. Okay, here I see an ester. There's no OH, right? The O goes straight to a carbon, so it's an ester. This is an alcohol. Here I see another ester. And then here I see an alkene. Is that it? Okay. So moving on. We're close to the end. A hormone is a molecule, steroid hormones. A hormone is a molecule that is synthesized in one part of an organism, which is then elicits a response at a different site. So we have steroid hormones made in one part of the body, and then once it's made, it elicits an effect at a different site. Two important classes of steroid hormones include sex hormones and adrenocortical steroids. Female sex hormones are called estrogens in general and progestins. Male sex hormones are called androgens in general. Okay, So here we're looking at female sex hormones. I'm not so great about the biology part. There's nothing to figure out. There are no mysteries here. It's just information. The estrogen, estradiol, and estrone control development of secondary sexual characteristics in females. They regulate the menstrual cycle and are made in the ovaries. So your ovaries are very important for female characteristics, right? So we have estradiol here and estrone. The progesterone is called the pregnancy hormone. It is responsible for the preparation of the uterus for implantation of the fertilized egg. So this is important. And of course, doctors monitor these amounts, and they can tell when a woman is pregnant by monitoring all of these. Anyway, this is progesterone right here. Okay, testosterone and androsterone are testes. They control the development of secondary sex characteristics in males. And these are these two right here. And we have synthetic analogs called anabolic steroids that promotes muscle growth, right? Muscle growth, some people take this so they can grow their muscles faster, right? They have they have the same effect as testosterone, but are more stable, so they are not metabolized as quickly. They have come to be used by athletes and bodybuilders, but they're not permitted, right? People have lost medals over this stuff, y'all. They have lost medals. Some of the people that I really loved when I was younger, I'm like, you know what? I thought you was naturally great. I didn't realize you were enhanced great. Anyway, but are not permitted in competitive sports. Prolonged use of anabolic steroids can cause physical and psychological problems, aggression, depression, all that stuff. So here are some examples of anabolic steroids. Remember, anabolic means that they are synthesized. This is the stuff that people shoot up. Okay, 3 examples of adrenocortical steroids are aldosterone, cortisone. You know how you buy the cortisone cream if you have bites and stuff from Walmart? Cortisol, this is the stress hormone. If you're so stressed out, a lot of this deposits fat on your waist. Okay, so here we're told to identify the functional groups of atorvastatin. Once again, simvastatin. These are cholesterol drugs. Haven't I done this already? I did, didn't I? Yeah, I did this one here. My ester right here, ester, alcohol. So I want to do this again. Oh, by the way, these have trade names. Zocor and Lipitor right there. I already did that part, so you can just scroll back up and watch, or rewind and watch the video, because I already did that part. Yay! Close to the end. Aldosterone regulates blood pressure and volume by controlling the concentration of sodium ion and potassium ion in bodily fluids. Cortisone and cortisol serve as anti-inflammatory agents, which also regulate carbohydrate metabolism. So it's very important. That's why when you stress out a lot, sometimes stress can cause you to lose weight because it causes imbalance in your hormones, and it can really mess you up. Prolonged use of these steroids can have undesired side effects, including bone loss and high blood pressure. Yeah, bone loss if it messes with your calcium ions too. Prednisone, a synthetic alternative, has similar anti-inflammatory properties. So people who have what's that, chronic conditions, they usually prescribe prednisone to them. I've had prednisone a few times when I've had upper respiratory things, and I'm usually like, do I really need to take this? Yes, you need to take it. Oh, come on. Because I'm thinking about all these side effects, right? Anyway, identify the functional group in aldosterone. Classify each alcohol as primary, secondary, or tertiary. Okay, so I have an alcohol here. Let me find my carbon. This is my alcoholic carbon. It's attached to one of the carbons, so that would be primary. Oh, I have an alcohol here. This is my alcoholic carbon. It's attached to 2 other carbons, so this is going to be secondary. Oh, I wrote this too big. Secondary. So I have a primary alcohol, secondary alcohol here. This group here is an aldehyde. Aldehyde. And then this one here is a ketone. Ketone. Here I have a double bond. Oh, double bond is not called a double bond. It's called an alkene. I need to power through. I'm close to the end. And this right here is a ketone. Yeah, my brain is beginning to shut down. I'm like, don't shut down, brain. I'm almost done. Finally, we have fat-soluble vitamins. And earlier we talked about fat-soluble vitamins, and I mentioned ADEC, right? Fat-soluble vitamins essentially being fats, right? Vitamins are organic compounds required in small quantities for normal metabolism and must be obtained from diet. Vitamins are either water-soluble or fat-soluble. So the ones that are not listed here are water-soluble. One time somebody asked me in a class, if vitamin C, which is not listed here, is water soluble, vitamin C, can you overdose on that one? Can you take too much quantities? I'm like, yeah. It is water soluble, but there has to be water around for it to dissolve in it. You can take too much vitamin C or the other vitamins, vitamin B and stuff, if you don't drink enough water. It's important. I sound so preachy. It's important for you to drink enough water to make sure that we don't have issues with too much of the other ones, because there has to be adequate water to flush any excess out of your system. Okay. For the fat soluble ones, the four fat soluble vitamins are found in fruits, vegetables, fish, liver, and dairy products. Dairy products, right? Okay, these are stored in adipose cells to be used when needed. Here's the issue. Vitamin A, D, E, K. These, when you find the bottles at Walmart, they usually come with a warning. Consult your physician before you start taking these. And you can't just take whatever amount you want. You want to be very careful with these. Why? Any excess you take is stored in your fat cells. So what happens when you're losing weight? If you're not intentionally losing weight, these fat cells tend to break up. Not break up, but burst open, like burst, right? So if your fat cell has some vitamins in here, vitamin A, and it bursts open, the vitamin A now gets released in your blood, and now it's in your body. And so it's not easy, but you can overdose on these vitamins because your body doesn't flush out any excess amount. It actually stores the excess. So why is it much easier to overdose? Overdose on a fat soluble vitamin than a water soluble vitamin? Because remember, it gets stored in fat cells. I should say here, excess gets stored in fat cells to be released on a later date. Excess doesn't get flushed out. Okay, so the excess doesn't get flushed out, unlike the water soluble one that goes off with your urine. Okay. Okay, vitamin A is found in liver, fish, dairy products, and is made from beta carotene. That's what they say. Make sure you eat a lot of beta carotene for night vision. When I was a kid, I was like, night vision? I can see just fine at night. I was young. What was I talking about? Now I'm like, vitamin A. I wear glasses. But still, as I'm getting older, I'm like, couldn't see that? Where is that? That's a car. That's a person. It is needed for vision and for healthy mucous membranes, right? Vitamin A deficiency causes night blindness and dry eyes and skin. Okay, this is vitamin A. So you can see right here, right? Definitely nonpolar. Right? Very definitely nonpolar. Vitamin D. Vitamin D can be synthesized from cholesterol, and it can be obtained in the diet from many foods, especially milk. And it helps regulate calcium and potassium in the blood. A deficiency of vitamin D can cause rickets, bone malformation. I haven't really seen rickets in America, but back at home, I saw kids growing up in rickets. But thank God, after a while, when they played in the sun enough and they got vitamin D from the sun, the bones in their legs straightened up, right, from supplements and then being out in the sun and playing. Vitamin D, once again, non-polar, therefore fat soluble. Non-polar, fat soluble. Okay. Vitamin D is synthesized in the body from a steroid. Which of the steroid rings A, B, C, and D are intact in vitamin D? and which one has been cleaved. So if we're looking at this right here, what does it look like? If this is A, B, C, D rings from the cholesterol, I still see an A here, right? Because you see you have an OH here, that's A. This looks like it was B. If I bring this back in here, B got broken apart, and this is C and this is D. So I'll say the B ring was cleaved. This is just to let you know there's a correlation between vitamin D and cholesterol. Apparently, low vitamin D causes a lot of messed things in your body. I mean, so do the other vitamins and minerals. To be honest with you, just take them all. Take them all. Of course, talk to your doctor and everything, but just make sure you're eating quality food, right? Not just tasty food, but quality food. Vitamin E is an antioxidant protecting unsaturated side chains and fatty acids from unwanted oxidation. Deficiency in vitamin D causes numerous neurological problems, although it is rare. This is vitamin E, also fat soluble and nonpolar. K, finally, the last one. Vitamin K regulates the synthesis of clotting proteins, prothrombin, and deficiency of this leads to excessive fatal bleeding. I remember learning about this in biology when I was younger. Vitamin K is important for clotting. So when you have a wound, some kind of open wound, you want to have enough vitamin K to help you clot the blood so it can stop the bleeding, right? The clot is your natural, the body's natural band-aid, okay? So vitamin K is very important for that. And this is the end of the lesson. I made it to the end. So yeah, I will post this as soon as it's done encoding. You guys have a nice evening.